Thank you for this wonderful introduction. And thank you to the organizers for this wonderful workshop. So I want to present here joint work with Herman Goulet-Ouellet, Carl Friedrich Nyberg-Brodda, and Dominique Perrin and Karl Petersen. And the motivation comes, of course, from equidistribution. So we are given an interval. We are taken a chronicle sequence. And we know that equidistribution means that, given an interval, you visit as often this interval as the length of this interval. So you can see it from an arithmetic viewpoint, equidistribution, or from a dynamical viewpoint. You have as a dynamical system underlying it a rotation mod 1, and its unique ergodicity gives you this kind of property. So the question I want to address here is, can we go beyond equidistribution in the same way as Robert Tichy in his lecture mentioned that there were several ways to go beyond equidistribution? So here I want to combine also equidistribution modulo m. So what does it mean here? Where can I count stuff modulo m? Well, I can count the number of visits in this given interval modulo m. So that would give me something like that. For fixed capital N, well, first, for fixed small n, I count the number of visits modulo sum m. To do that, I need two levels of integers, so small n and a big N. So the question will be the following. Given some capital N, I count the number of integers smaller than capital N, such that when I look at the integers smaller than small n, such that the number of visits is congruent to some class. So I count the number of these elements. I want to see whether this means tends to 1 over m. So that's my equidistribution question, with these two levels of counting stuff. So there's a long story about this coming from ergodic theory dynamical systems, which started with Veitch and with culminated with work of Guénet, Parot, but I mentioned Stewart, Merrill, which has to do with skew products, as we have seen with yes, you're right. I was so much focused on my two levels of n. No, No, sorry, no, I don't, no, you're right. No, because I've got, in fact, two parts, an equidistribution. So, no, when I give a lecture, you can ask any question, I will say yes, and so be careful to answer. So I need to concentrate. For this modulo m part. So you've seen some skew products this morning, so you can, and we'll use them. So we can see that we'll do some kind of skew product on what happens with the I distribution and the modulo M, the group distribution. And this, as I said, this question started with the work of Veitch on this kind of object. So that's my main question, for which it will depend on the length of I, because you visit I, so. And it depends on I, it depends on alpha, and there is a rich characterization and story of characterizations of the parameters alpha, the length for which we have such equidistribution, and things are expressed in terms of Ostrowski numeration as usual, and nice characterizations that you can find in the archive paper by Guénet and Parot, for instance. So that's my motivation. And then, so to tackle this kind of questions, I will go through symbolic dynamics, use the Fibonacci shift, of course, as an example, as a guideline. We'll go through skew products. And then I will shift the viewpoint to more language viewpoint, and then we'll see arithmetic applications. So, Sturmion, of course. So focusing on the number of visits to an interval, when this interval has some specific length here, length, say, 1 minus alpha, corresponds to the Sturmian world, Sturmian codings. So we know that visiting an interval, specific one, as I said, I not, interval of length 1 minus alpha, can be very well understood in terms of symbolic dynamics by coding trajectories with respect to the visits of this given interval. And then we don't lose that much information. It's not ridiculous in the sense that we have an isomorphism between the dynamics of the rotation plus alpha mod 1 and the dynamics of the shift on the set of Sturmian words. This isomorphism is only in measure, but there's commutation of the dynamics. Well, it's not ridiculous to try to understand equidistribution properties from this symbolic viewpoint. No. If we continue to think in terms of equidistributions for symbolic dynamics, the natural notion that corresponds to this discrepancy that we've seen, the comparing number of visits, if we renormalize it, corresponds to this symbolic discrepancy. So first, I need to introduce the notion of frequency of occurrence of a letter in some sequence. Well, that's the number of times you see one given letter divided by the length of the prefix you consider. And then discrepancy corresponds to compare the number of visits, the times of you see a letter A. So if you code your rotation with respect to some interval I, if you put the letter A when you visit A, you recognize the number of visits to I. So here the number of occurrences of letter A minus n first times the frequency minus the expected value. So that the symbolic counterpart of this discrepancy notion that we've seen in terms of visit to an interval. And then we can count factors, also occurrences of factors, and try to find words which are super well equidistributed in the sense that this quantity is bounded. This corresponds also to the balance property or the abelian complexity. It's the supremum on all the prefixes. Yeah, exactly. It has no reason to be bounded, but for some words, it can be bounded. So you take the in the same way as we took the n first n alpha, the first n terms k alpha, and you want to see how often you visit an interval. That's the same. You take the first n letters of your word. You see how often you find the letter A. Yes, exactly. And that's what exactly, that's on the prefix. Exactly. Yeah. And then we have finite alphabet, we take the max on all the letters. And then you can also take a count. And if you really want to have an equidistribution theory, in the same way as you take the maximum, the supremum on all boxes in discrete distribution or intervals, then you take it would be fair to consider also factors. And then, yes, I was saying that it's related to the abelian complexity discussed by Pierre Popoli, which the fact that the abelian complexity is bounded corresponds to the fact that this quantity is bounded for the Fibonacci world. So that's a symbolic viewpoint. And then if we think in terms of what it means to be equidistributed, we can go into two directions. For instance, we can, given an interval I, checking. So I do this va-et-vient between symbolic dynamics and codings of visiting an interval. So if I come back to my original word of n alpha and a given interval, I could focus on so-called bounded reminder sets, the intervals for which the number of visits is modulo some constant equal to the expected values, ni. So these are very good intervals with respect to alpha. There's a lot of nice theorems on this. And Kesten proved, for instance, that an interval has bounded reminders is a bounded reminder set if the length is related to alpha. Length is in alpha z plus z. And then you can ask how small the discrepancy can be. Still in the flavor of the results you have on abelian complexity, it's super interesting to have small constant balance. So you can go in this direction, and Maria Clara Werneck has nice results on the fact that in the Fibonacci shift, you kind of words with very small discrepancy. But the direction where I want to go now is this modulo M adjunction in terms of equidistribution. And since there were a lot of lectures about logic, I just wanted, with the next slide, to stress the relations that we have between dynamical systems, automata theory, and number theory through logic by recalling a few results. And why I'm recalling that is to say that equidistribution has also something to say for the logic results we've seen. So we've seen results about Pressburger arithmetic, first order logic, Walnut. And then the idea was to see whether we could keep decidability. We could by adding some numeration system like Piso numbers and stuff like that. So I wanted just to recall that there are very nice results by Hieronymi and his co-authors showing that if you put in first order logic all the Sturmian words, then you keep decidability. And to prove that, the idea is to play with not the leading digit, the behavior of leading digit like Bedford laws, but the behavior of the second leading digit. And there are nice arithmetic questions behind in the proof of this result by Hieronymi. And then if we go to MSO, so MSO, we discussed that, someone discussed that in this week. So you have the right to quantify about on sets. So you have the modulo M possibility to express terms in terms of modulo M. Then if you take a Sturmian word, a decidable, an effective Sturmian word is you can compute the slope, the continued fraction of this Sturmian word. Then you keep decidability even in MSO theory. And what the proof, the argument which is behind is just to say that if you add to some MSO theory a predicate, my predicate PS is just to say you can say whether the value at the nth term of the sequence. So if you want to add an infinite word as a predicate into a logic, knowing whether you are still decidable comes to the fact that your infinite word is uniformly recurrent. So this is it's a result by Semenov, and it's quite striking. A decision problem has to do with an equirepartition problem or an ergodic vision of stuff, which says if you add some predicate, so your predicate is some way to select elements of a set of natural integers, and you have an infinite word which code this set of integers you're taken. The characteristic word of this set of integers is an infinite word on 0, 1, say. If this infinite word is uniformly recurrent, that is to say that you see every factor with bounded gaps, then you keep decidability. So this is a super nice application of equidistribution in something completely different. So with the same set of co-authors, for instance, we solved quite long-standing conjecture on the fact that if you, in MSO, you add the right to express, to use powers of 2 and powers of 3 at the same time, you're still decidable. And our proof, well, I sketch it, remains to say that, okay, combining powers of 2 and powers of 3 corresponds, in fact, to have a Sturmian word of slope log 2 over log 3. Combining powers of 2 and powers of 3 is to see how you can order them with respect to themselves, how you put order if you add powers of 2 and powers of 3. It's given by a Sturmian word. A Sturmian word is uniformly recurrent because it's uniquely ergodic and stuff, equidistributed. So our proof comes back to this kind of properties. And if we have powers of 2 and 3 and 5, then we need some transcendence information channels conjecture. So for instance, to just give a more concrete flavor to the kind of statement we can express is, if you want to see whether 3 consecutive powers of 3 to the n, 3 to the n plus 1, 3 to the n plus 2, whether you find 2 consecutive powers of 2, okay, so can you find infinitely m and n such that you have this kind of ordering, plus some modulo, so that's MSO flavor, so modulo expression. You can express it in MSO and you can answer this kind of question. So with this logic and equidistribution slide, I just wanted to repeat the fact that equidistribution properties of some sequences ergodicity of dynamical systems which are behind. Minimality, sorry, I'm saying ergodicity. In fact, it's minimality of my rotation, which is important, which gives uniform recurrence, can give you some nice predicate that you can put in MSO theory, and for which you can express nice properties concerning these infinite worlds, like this example. Equidistribution has also to do with logic. But now I come back to my question, and so my question about equidistribution mod M has to do with skew products. You're not surprised after this morning talk, I guess. So you've seen skew products. So we start with a minimal shift, like a Sturmian world, which codes some hitting some coding of rotation, for instance. So start with a minimal shift, enter group, and embed your shift or your alphabet in the group via non-two morphism. So you put the letters into a group, and then you make a skew product, which is a usual construction in dynamical systems. My colleagues come from are more algebraically oriented, so I lost the fight in being able to put my shift first. So that's life. So here, the algebraic part is on the left, and then the shift. But if you think in terms of skew product, the main dynamics is the shift. That's the dynamics which governs everything. And then you get a skew information on the left on the group. It's a way to skew a shift, to embed a shift in a group in some way. And then if we take we start with a Fibonacci shift, and take the group which correspond to seeing parities, then we can embed the letters in, by saying when you see a A, you put a 1, when you see a B, a 0. And then with that, you can count things modulo 2 in the Fibonacci shift. So what is the relation with the beginning with the Fibonacci shift? The Fibonacci shift is a Sturmian world, so it codes the number of visits of the rotation by the golden ratio mod 1 on some interval of length 1 minus the golden ratio. So knowing, counting modulo 2 in the Fibonacci shift has to do with my original question, which was to see how often you visit an interval modulo 2. So we have such a skew product, the shift on the right, and the information that you get is acting on the left, on the group, by some map which replace a letter by a member of the group, and x0 is the first letter of my infinite world. So I've got an infinite world. I take its first letter, I put it on the left, I act on my group via my morphism phi on the group, I shift on the right, and I continue to do that. So I've got cocycles, but I decided not to give the cocycle equation, so but you got it from this morning. So when you iterate this operation, when you iterate your shift, your skew product, you have shifted on the right your word, but what you've done on the left, on the group, well, you have multiplied by the elements prefix of the sequence A to C. So you have an element of your group, G, and you do phi of the first letter, second letter, and so on and so forth. So let us check that it has something to do with the original question that I put in orange again. If I consider my Fibonacci shift that I embed in Z over 2Z, by replacing, as I said, letters A by 1, letters B by 0, on the group part of the group component of my skew product, what I have is that I count number of occurrences of A's modulo 2, because when I see a B, I do nothing. So I changed notation. I was in multiplicative notation. Here I'm in additive notation. So on the group part, what I do, if I start from 0, well, I just see the number of A's that I see, and I consider the parity of the number of A's that I see. So I consider it modulo 2. So above it was multiplicative division, here on Z over 2Z. So what I'm claiming with this new dynamical system, I've enriched my shift, which is a group part, which does what I want to understand on my group part, because it will count the number of visits to some given interval. So from a dynamical viewpoint, knowing how this works, well, you recognize here a Birkhoff sum. You have 1 over n something. So I claim that understanding the ergodic properties of this skew product, the minimality and the ergodic properties of this skew product, will answer my problem. This problem here in orange corresponds, well, will be solved if we know, for instance, that the skew product is minimal and uniquely ergodic. And that's the approach developed by Veitch originally. So, since I mentioned a little bit of ergodic properties, I need to make some ergodicity to have to clarify the probability measure. So it's exactly as this morning. A natural way to put a measure is to take a measure coming from your shift on the right, and then to put a counting measure on my finite group on the left. I should have stressed the fact that I work with finite groups. So this morning we were with Z. Here I'm much more focused. I work with finite groups. It's much easier in this sense. And then we get an invariant measure by taking the product measure of the measure coming from my shift by the counting measure on my finite group. That's a possible measure, but you have a lot of other measures that can exist on your skew product. It might not be uniquely ergodic. We expect it to be uniquely ergodic, but it might not be uniquely ergodic. So now we have an idea of our object, this new dynamics. Okay, so let's take an invariant measure on the skew product. We saw that we can make one with the counting measure times the measure from the shift. Fix an element of the group. So let's do ergodic theory. We might not need to have ergodicity. We have at least at our disposition the pointwise ergodic theorem that says that if you take almost every element with respect to the measure of the global, the enriched shift, the skew product, well, ergodic sums converge towards something which depends on some function. Yes, so here I took a very particular observable function, the characteristic function of visiting one element of my group. I already have an automaton viewpoint. Okay, so that corresponds to the problem I had. I wanted to see whether something is even or odd. Well, that's corresponding to visiting one element of my group. 0, if I want to see if something is even, with respect to these dynamics. Okay, that's not super efficient for the moment, but so start with element 1. If we were in additive version, that would be 0, counting modulo something. So here, start with element 1 of my group. So I forget about my H element, which is here. So replace it by 1. And then the fact that we work in a group allows us to make some easy manipulation that tells us that now we can go from a result that is true for the global structure that holds for the shift, which is in fact what we are interested in. The measures on the whole group might not well project. They project. Okay, sorry, but it's better to understand what works directly on the shift itself. Okay, so the fact that we work with a group allows us to say that these sums converge towards something which depends on my element of the group. Okay, so I've got finitely many functions like that. That's where I am with the use of ergodic theorem. So here. So then, in fact, the fact that the group is finite makes everything, that's what is behind this simple argument, but the fact it's a group. And our target of finite group. So now we have, so exactly as Tom observed, we have a transfer of genericity. So now we can do something natural. So we can take, as in ergodic theory, the mean behavior of these functions, and then we can invert our integrations, the Birkhoff one and the spatial and temporal viewpoints. And then we observe something, which is that this here depends only on the first coordinates. By definition, the skew product sees what happens on the first coordinates. So to understand how it behaves when we integrate it on the shift, it's just to understand how it behaves on cylinders of size A. So we understand this value, this mean value, on the shift of this behavior like that. But this gives us the idea of considering some particular languages, rational languages, which are pre-images by my morphism of one given element of the group. And so what I claim here is that this quantity can be reinterpreted as this Cesaro mean of the measure of elements. So the measure is given by with respect to my shift of elements of a given size which belong to some particular language. So I've shifted from a language viewpoint. So a language viewpoint could be counting words which have an even number of A's, for instance, typically the example I have here. So I enrich here this ergodic viewpoint with a viewpoint from language theory, because a language which is the pre-image of an element of a group, it's a rational language. You can describe it via a super nice automaton, which is a group automaton, which corresponds to a Cayley vision of your finite group when you put as vertices your element of the group, and then you put as vertices elements of the group, edges between two vertices, the elements of the group which act on the elements, and you can get a graph from a finite group. So now we have a vision enriched with language and rational language vision, which says that the ergodicity of our skew product not only can help us to answer our question, but allow us to describe this object, which is understanding a given rational language of a specific form under the viewpoint of a measure, or testing a given measure under rationality. We have two viewpoints, so that gives information in both senses, either on a shift, on a measure, or on a rational language. So I've given several times this lecture, and sometimes I introduce this notion first that I will introduce now, this general motivation. And sometimes I start from the skew product viewpoint, saying that with this question on equidistribution considered from the group viewpoint, we can arrive to some concept which makes sense in rational language theory. And if we come back to the Fibonacci shift, everything works well. We start with a minimal uniquely ergodic shift, and when you take a skew product with respect to a finite group, we are still minimal and uniquely ergodic. And then, so it has to be proved. We use, for instance, the fact that this enriched shift is again a substitutive shift, and then we have a primitive matrix again behind, and then we get a unique ergodicity. So I've got other colleagues who look also at this problem, Olivier Carton, Vincent Delecroix, and Thierry Coulbois. And the way they see that is that they input the Fibonacci word in some automaton. We'll see it in a few slides. And they also have results on unique ergodicity with other ways of proving that. There are several ways to prove that. And I claim that with my previous slide on the ergodicity, the fact that my skew product is uniquely ergodic says that I can answer in the Fibonacci case, that is to say for golden ratio and the length of interval related to the golden ratio, that the number of visits equidistributed. That was my orange question from the beginning. There's the number of times you visit an interval takes all the congruence classes in this equidistributed way. So this theorem answers my original question from equidistribution. But now I shift to this other viewpoint, which is the following. I'm given a shift, and I want to see whether we have a notion of density, frequencies for patterns, which are not only factors that I see. So a pattern is a word with an even number of a given letter. That's always my same example. So given a shift, can we evaluate, is there a good notion of density for counting not only factors of a given size, but factors with this kind of description, a rational description, a rational language description. So I'm given a shift. A shift, as often, I take an invariant measure on my shift. So invariant measure means that you can prolongate the values that you give of on you measure on cylinders on the right and the left, and it behaves well. So if you think in terms of language, with the question on understanding densities in languages, it might be natural to take a Bernoulli measure or a Markov measure. But here, with a shift, what I want to start with this slide, just recalling some basic fact about shift invariant measures, but I want to say that understanding a language with a shift means that you have a lot of new measures which behave differently as a Markov measure. These are completely different types of measure if you take a zero entropy shift, for instance. And then I will define this notion that we have already seen with the pointwise and the ergodic viewpoint. Now I start with a shift, which gives me a measure. I start with a language. And then I can ask, what is the density of such a language? Remember, the language is, for instance, a number of set of words, such that the number of occurrences of A's in these words is even. So such a rational language. So how can I define such a density? Well, a natural way is to look at the elements such that prefixes are in the language. That is to say, another way is to say we measure the elements of the language, and we take which have a fixed length, and we take a César mean to have such a density. So we will see that we are obliged to take a César mean. In fact, the existence of this density without the César mean would correspond to mixing properties of the measure, of the shift. But then that's a notion of density for rational language. Okay, you measure things in your shift with respect to a measure which is a priori given by you measure the frequencies in your language with respect to a measure which is given by a shift, which has nothing to do with your language. You can start with a shift like a Sturmian shift. You can take a rational language, and you mix two things. So this notion dates back to the 70s, I think, with work of Berthé and Schützenberger, and in this case, they used for the measure, Bernoulli measure, as I said. So they wanted to understand the density of rational language. And then I stress the fact that since the measure sees as for support the shift by definition, you see only elements in your language in your shift. So the measure is a way to extract from the shift, so from the rational language, the big language, elements of your shift, which is a priori small if you take a Sturmian shift, small in terms of zero entropy, as I said. So you can take an exponential language with exponentially many factors of a given size, and you want to extract information with your measure from a shift which has maybe a linear factor complexity, and you want to see, even if you consider this global set of elements from this viewpoint, you want to see whether this quantity exists. So that's a question from the rational viewpoint. So I continue with my example from the beginning. So what is the density of finite words having an even numbers of A's in a shift, in the Fibonacci shift, say? So that's where an automaton viewpoint can come. So as I say, with the group Z over 2Z, I can associate this graph. The elements, the vertices are elements of Z to Z, and then the edges correspond to the action +1 modulo 2 on these elements. And then I can embed my Fibonacci shift. So I just repeat this graph, this automaton, by replacing letters by the value. And then I feed this automaton with Fibonacci words starting from 0. And then it gives me, the states give me this value that I'm looking for, how many the many A's I've seen in the prefix. And then if I look only at the pre-image of 0 by my morphism, it corresponds, well, when you stop at 0 in the prefix, it means that you have seen an even number of A's. That's what you see on the graph. So that's another viewpoint on my skew product. My skew product means I feed, so on my group part, I feed a particular Cayley graph structure, natural structure associated with my finite group. I feed it with a shift, and I want to see whether I equidistribute in the states. So the corresponding statement of my skew product behaves well, is uniquely ergodic, is to say that, well, the sequence of states that I visit when I feed this automaton, this group automaton with the Fibonacci shift, well, the sequence of states that you visit is equidistributed. So that shows that this notion of equidistribution is robust when you start with the Fibonacci with respect to group distribution. That's what I meant by group equidistribution. And just with this slide, I wanted to emphasize the fact that if we would not have taken César mean, but this, since we have no mixing properties in the Fibonacci shift with this measure, then we wouldn't have a limit. So we really need to make such a counting, such a notion of density to take César mean. So what I mean by this is if I count so these words which have an even number of A's, then there are moments in my languages, if you take the words of length Fibonacci sequence for n, then the density tends to 1, and if you take words of length Fibonacci for n plus 2, the density tends to 0. So there is nothing nice here. We really need to leverage through a César mean through a Birkhoff sum, as we saw before, which makes sense. But if you would have taken a Bernoulli measure or a Markov measure instead of taking a measure which comes from a Fibonacci shift with the same language, the same group language, we would have a convergence without César mean. It's 0. It's really that we are paying the fact that the absence of mixing in this translation, coding of a translation that Stomian shift is. And so now I arrive to this question. Remember, I started with an equidistribution question. Now I arrive to this more general question about a language, a rational language, a group language, a language described by a group. Does this limit always exist? We've seen that it existed with Fibonacci, but it may be not sufficient to have a general statement. And can we compute it, in fact? Can we have nice expressions for this? And knowing that, yes, the first results in directions come from the 70s from Berstel with a rational language viewpoint, theoretical computer science viewpoint. So the results we have is for group languages. So phi minus 1, where phi is a morphism. When you embed with a morphism your alphabet into some group in a surjective way. So if you have some group structure, well, the density exists. And if you have ergodicity on the skew product, you have a very nice equidistribution in the sense that if your language is given as, is described by the pre-image of a subset of groups, then the density corresponds to the number of elements of the group you see divided by G. That's your generic feeling, Tom, that's here. It equidistributes super well. So if you have ergodicity on the measure of the original measure times the counting measure, okay, you have super good equidistribution. But if you don't have ergodicity, if you start just with an ergodic measure on your shift space, well, the density still exists. So I haven't written here, but here in this statement, we've been recently a step further by taking instead of a group, a monoid, a semi-group. A rational language is a pre-image of some part of a finite monoid. So we still have the existence of a density, but we have no ergodicity which is behind. We prove it with completely different arguments, completely algebraically. So what I want to say here is that the existence of density is always true, even if you take rational language. It's not a question of ergodicity, but the ergodicity or the equidistribution enters into play when you want to have something which behaves well in this sense, when you want to have equidistribution, which is fair, in fact. Ergodicity has to say something about equidistribution and in general, if we take any weird rational language which is not associated to a group, then we don't have such nice formulas. And so just in the case of a group, the proof is just that we use an ergodic sum. That's the slides that we've seen before. So the proof is just in the case of ergodic skew product. It's just what we've seen before with the ergodic theorem. So I just want to stress the tools that we use, in fact, because we've seen several kinds of ideas. So as I said just before, in the monoid case, for the existence of the density, we are completely algebraic. We use properties of the semigroups, Green relations, G-class, I don't know whether it rings a bell. So it's a way to decompose finite monoids, finite semigroups, with respect to the two-sided ideals or to the ideals that are generated. So it's a decomposition of semigroups. We are here on finite semigroups, completely algebraic. But there's a group which is hidden here in this decomposition with egg boxes and stuff like that. So we are able to detect in a semigroup a group. And we come back to the group case. But it's algebra looking for a group. There is no ergodic theory here for this general case saying the density exists for rational language. But now, once we have a group and we come back to the group case, then for the skew products, we have several properties, minimality. Then for the minimality, it's combinatorial. We can express it in terms of written words. We have seen the concept, I don't know which lecture, but you've already heard of written words. So we can do that in a combinatorial way. And then, in our case, ergodicity, we explore it with respect to Anzai's criterion, which is a question of co-boundaries. But other people do that with essential values, and I will give an example of this later. And just to finish, as applications, what kind of arithmetic applications can we do? By feeding some group with Fibonacci. Okay, so Fibonacci, we've seen it, it behaves well. So it answered the question from the beginning. Numbers of visits of an interval, congruence of the number of visits behaves well. That was my original question. It's solved. Is to embed now Fibonacci in continuous fractions. So to do that, I replace matrices I replace letters by elements of GL2 of Z, ideally. But since we deal for the moment only with finite groups, that will give us information on the equidistribution of partial quotients. When you feed a real number, when you get a real number whose partial quotients are given by the Fibonacci word. So I take, for instance, 1, 2, I want to, an odd and even number, I could take 2, 3, any kind of stuff. You replace the Fibonacci word on AB by a sequence on an even and an odd number. You put it in GL2 of Z over 2Z, and your morphism is on 2. So what you do here is that, well, you get the matrix that we've seen with Hitoshi's lecture and many lectures. Okay, and then we are looking at these quantities, Pn and Qn, modulo 2. And then the theorem, the equidistribution theorem that we have just says that we recover what was known for Jaeger and Yarde and proved that with essential values for these results. They prove that, we refine that the equidistribution properties of real numbers, proven in terms of essential values, here can be proven in really combinatorial ways, can be proven to satisfy the same equidistribution result. So you might wonder why 1/3, 2/3. It's GL2 of Z over Z has 6 elements. It's S, the group of permutations on 3 elements. So you can make your graph with your 6 elements. And then, since the determinant of the matrices is 1, if you look at your 6 matrices in this group, when you look at the place of Qn here, it's more likely here to find something which is odd than which is even, just combinatorics of the group of 3, the group of permutations on 3 elements, or GL2 of Z over 2Z. And then I just end with this. The fact, so this nice application says that feeding with something super well ordered like Fibonacci continued fractions give you a behavior that mimics the generic behavior in terms of equidistribution of partial quotients. And then you also have, in the same way as you expressed the Levy constant, Tom, in your lecture, the existence of a Levy constant, which is not, it exists at least. It obviously cannot be give the entropy. But for these elements, using results by Walters, Fan, and Wu on existence of Lyapunov exponents, the product of matrices governed by Fibonacci world has also a nice Lyapunov behavior, and you have also a nice Levy constant. So we recover this kind of ideas that putting Fibonacci in a real number gives you something which is transcendental, or in terms of normal numbers. Well, an algebraic number has to be normal and stuff like that. So we recover the relation between some super organized Fibonacci, which gives you a kind of random generic behavior. Thank you.